Thank you.
No problem.
Right, now we can start. And so I was asking about questions about project number 2, 3. I'm going to start to grade. I already graded number 1. You can see my comments in there in the PDF, and I will upload the solution as soon as possible so you can compare the solution to whatever you have done so far. In the solution also you will find very useful Python code that you could use for your own solution. You don't have to use it. It's not a requirement. But if you do use Python, or if you want to learn to use Python, you can check that code and use it for this particular project. Okay, and number 2, I will be grading that early next week or towards the end of the week if I have some time. All right, so let's see. The last thing we saw was about how to characterize an anisotropic medium and how to measure the 5 components. No, not that one. This one. How to characterize the 5 components of a vertical transverse isotropic medium. And we're going to finish with that today. And we'll also see the applications of that. So let me get there, get organized, and let's close this. Okay, so we talked about the static coefficients that we measure with a triaxial cell, and we also talk about the dynamic coefficients that we measure with piezoelectric sensors, and those have very tiny movements. And with those we measure elastic waves. We measure how the velocity travels through the rock, how long time it gets to get from one side to the other, and the length divided by the time give us the velocity. With those velocities and with the density of the rock, we can calculate the stiffness coefficients. And we also talked about the Young moduli in samples that are perpendicular to bedding and parallel to bedding, and said that in the absence of fractures, always the horizontal Young modulus EH is going to be larger than the vertical Young modulus EV. In order to understand a little bit better the anisotropy of rocks, there are a set of parameters that were used in geophysics that help us characterize anisotropy with some dimensional numbers. And these are called the Thomsen parameters. And they are very useful to characterize different types of rocks and in order to get to know how anisotropic they are. The Thomsen parameters are 3 parameters: epsilon, gamma, and delta, and they are defined as, the first one is the difference between the stiffness coefficient in horizontal direction minus the stiffness coefficient in vertical direction divided 2 times the stiffness coefficient in vertical direction. Is this value going to be positive or negative for TVI media in the absence of fractures? Which is larger, C11 or C33? C11, right? So this is going to be positive. This is going to be positive, and it goes in general from for anisotropic rocks from 0.1 to 0.4. If we express these stiffness coefficients in terms of velocity, remember that the stiffness coefficients is density times velocity squared, but density is going to appear everywhere, so I'm not going to even write it because I know that it's going to cancel out. This is the p wave velocity in horizontal direction minus the p wave velocity in vertical direction, both squared, divided 2 times the p wave velocity in vertical direction. So the first parameter characterizes the anisotropy in stiffnesses in horizontal and vertical direction and tells you how much stiffer, when it is positive, it is in horizontal direction than in vertical direction, and for media that are not fractured, it's going to be a positive value. The second Thomsen parameter is written like this, and you tell me what it means physically. What do you think is trying to quantify? Shear, yeah, which shear? C66 is the shear velocity in the plane 1, 2. And C44 is the shear stiffness in this case, or the shear modulus, in direction 1, 3 or 2, 3. Usually, also, that's going to be a positive number. And that one characterizes the anisotropy of the shear velocities. Usually, in this type of media, there is a type of velocity which is, one is faster than the other, so there's going to be the fast shear wave velocity and the slow shear wave velocity. And that parameter characterizes that. And the last parameter is the parameter delta, which is a little bit longer, and it is written like this. The first two are kind of easy to remember what they are and also to interpret them physically. But the last one, it's a little bit more complicated. I was thinking about creating an animation of this, but I didn't have time to do that today. Probably will try to do that soon. I'll send you the link in order to show what is delta. But delta is going to characterize what is the ellipticity of the p wave velocity. So let me explain what that means. Let's plot in the y-axis the velocity in direction, the p wave velocity in direction 3. And let's plot in the x-axis the velocity. Well, no, actually, let me call it. It's going to create some confusion. So just let me call it x and y, where I have a medium which is layered, and I'm adding here a coordinate system xy. So when I'm in the x direction, the p wave velocity is going to be the horizontal velocity, and let's say it's a value somewhere over there. When I am in the vertical direction, the p wave velocity is going to be the vertical velocity, and we know that that's going to be lower than the horizontal velocity. If I measure the wave velocity at an angle theta, that's going to be some value which depends in these two. And this equation is going to be something close to an ellipse, but not quite. And the ellipticity of that ellipse is going to depend on that parameter gamma. Sometimes you may have this shape, which at this point it may be a little bit closer in this direction or a little bit further in that direction. It's not a perfect ellipse, and that's the parameter that controls that. And it depends on the value of the wave and the p wave velocity at 45 degrees. So that's the third parameter that controls the anisotropy of the medium. In general, for something which is called weak anisotropy, in which the parameters epsilon and gamma are not too large, we can write this equation, and the p wave at an angle theta is going to be a function of delta, a function of the angle, and also a function of epsilon. Remember that gamma was for shear wave velocity, and for the shear there is going to be something similar too. But for the p wave, this is the equation that explains that kind of ellipse. It's not perfectly an ellipse, and this parameter delta is the one that controls the shape of that. So in general, it's a very good idea many times to measure these parameters and to characterize the rocks according to epsilon, gamma, and delta, because then you can group them and you can analyze them and derive some common behavior out of them. All right, so what do we do now with all this anisotropic theory? Well, what we want to do is we want to do the same thing that we did for the isotropic medium. And that is having a stiffness matrix, and with that stiffness matrix, derive what would be the state of stress for a given load or overburden and a given tectonic strain, which in this case I don't have the tectonic strain, but this is the equation for tectonic strain. And this is for isotropic media. But we know very well that some rocks, most rocks are not isotropic. And if you were to calculate the stresses with isotropic theory, in many places, it will be far off the real answer. So in order to get closer to the actual answer, you need to use something a little bit more refined. And that's going to be the anisotropic theory. So what we're going to do is we're going to write what are the equations for anisotropic media, and it is exactly the same thing as with the isotropic media, but with an anisotropic matrix. All right, so let's do that. This is going to be the 1D, still 1D, mechanical Earth model with anisotropic parameters. All right, the first thing I have to do is I have to write the stiffness matrix and for strains as a function of stresses. So I'm going to have here the minimum tectonic strain, horizontal strain, here the maximum tectonic strain. I'm just going to refer them with H lowercase and uppercase, and here I'm going to have the vertical strain. I'm going to neglect the shear strains because I'm going to assume that vertical stresses and horizontal stresses are principal stresses, and I don't have any shear stress or strain. So if I just care about the linear strains, then this matrix is going to look like this. Let's try to write it together. You will see it's not too difficult. And here I'm going to put sigma h capital, and sigma v. Okay. Which MEM modulus relates horizontal strains to horizontal stresses? The horizontal MEM modulus or the vertical MEM modulus? Horizontal, right? So here we're going to have horizontal. And here also we're going to have horizontal. The same way, if you relate vertical strains to vertical stresses, the coefficient is the vertical MEM modulus. Similarly, if you relate a horizontal strain in one direction to a horizontal stress in a perpendicular direction, but it is still in the horizontal plane, here we're going to have a horizontal Poisson ratio, and here a horizontal MEM modulus. And when we relate horizontal to vertical, now we have the vertical Poisson ratio and the vertical MEM modulus. Notice that this matrix is very similar to the one we wrote before for isotropic media, but the difference is that now we have these subindices that refer to horizontal and vertical directions. Okay. The next step is going to be to solve for the vertical strain. That's the same thing that we did before for the isotropic case. And then what we want to do is, instead of using a vertical strain in the equation, since we don't know that, we want to replace it for vertical strain as a function of the vertical stress, because that's something that we know. We compute total vertical stress, we compute pore pressure, we know effective vertical stress. And then after we do that, we replace that into the two top equations, and I'm going to get these two stresses as a function of these two strains and as a function of sigma v. It's the same thing to what we did before. But here we're going to do one more thing. And again, it's all just math. If you want to check it later on your own, you're welcome to do that. It took me like 4 hours sometimes. I did it because I had some small mistakes that it took me some time to see where those were. But believe me that these are the equations. I'm just going to write them out, but there is one more thing that we're going to introduce today, and it's something we're going to see in 2 weeks. For the effective stresses, we're going to add one more thing, which is the Biot coefficient. And in this case, it's going to be a Biot coefficient in horizontal direction. Let me finish the equations. Writing the equations, I'll tell you what this Biot coefficient is about. But it's just it's just the effective stress equation corrected by a coefficient. And this is with pore elasticity, and this is what we're going to see in about 2 weeks, where alpha H and alpha V are the Biot coefficients. Biot coefficients, alpha, are when the rock is soft and all the deformation you put goes into changing porosity. It goes to value equal to 1. When you deform the rock and when you deform it, there is a fraction of that deformation that also goes into deforming the grains themselves. The Biot coefficient goes to a value less than 1. We're going to see in detail about how to measure this Biot coefficient later on. But in general, it's a value which is close to 1, and it corrects the effective stress equation to have a more accurate value that considers grain compressibility. All right, so that's the only thing that, that is new for now. And once I solve for this and I put it into that, the final equations of horizontal stresses with an anisotropic model are going to be the following. The minimum horizontal stress, total, remember here I'm writing total, is going to be the pore pressure corrected by Biot coefficient plus it's a little bit longer than the other one, but not a lot different. Okay. I'm just checking that the equation is all right while I write it. Now the tectonic strains are just in one term over here. Okay, that's for the minimum horizontal stress, the maximum horizontal stress is going to be this. Let me know if you see something that it doesn't make sense. But probably you recognize this is a plane strain modulus, but now in horizontal direction. Compared to the previous equation, we have an additional term, which is this one, due to anisotropy. And finally, an equation that we know already very well. I found a mistake in my notes. This is just bulk G dc. So we already knew that equation, and these are the two new equations for horizontal stresses for an anisotropic medium. And with that model, now we're going to be closer to predict stresses in formations that exhibit anisotropy. Just to complete, well, I guess you're copying. Some of you are copying. So while you're copying, let me do a little drawing here, just to make clear that this is about anisotropic media. Okay. So what do we do with it? Check if you have the first project where I gave you a stress log. And in the meantime, I'll open that paper in here. Come on. It's a little bit slow. All right, there we go. So here we want to look for the paper, which is SPE 180 965. 9965, thanks. And this is this paper. And here, let me download it. And open with Adobe. All right. No, what did I do? Okay. All right. So in this paper, they use this anisotropic model. And it's the one I used to give you the first assignment. Here you can see the matrices that we have used: stiffness matrix, compliance matrix, the equations that allow you to calculate those moduli as a function of the stiffness coefficients. Here is the effective stress law with the Biot coefficient. And we'll talk about this later on. But where I want to go right now is some of what we already discussed too. Here you have a plot of, for example, sigma 3 in the y-axis, static values, and also for C1, 2, and C1, 3. With these equations, you calculate the static values as a function of the dynamic values based on correlations. And here you have first track, a model calcite, second track, vertical Young modulus, then horizontal Young modulus, vertical Poisson ratio, and horizontal Poisson ratio. So with these and with the equations that we saw, which are exactly the same as the ones that I just, the ones here as the one in the paper, you can calculate the stress as a function of depth with an anisotropic model. So you already have the solution. This is the solution, right? These are the stresses. We don't have to go step by step to verify that that's true. But I just wanted to come back here and take a look at the anisotropy of this rock. Look at the Young modulus in vertical direction and the Young modulus in horizontal direction. Which one is larger? It's the same scale. It goes from 0 to 10 million psi. I don't think so. Look, for example, let's look at this right here at this depth, the horizontal is about 10, and the vertical is about 8 for that spike, second spike from the top. Here, and it's also, no, this is in linear scale. Here in the 6th track, you have the anisotropy of the Young modulus. This is the horizontal Young modulus divided the vertical Young modulus. So here you can see a little more clearly anisotropy. And you can see that it goes, in this case, from 1 to more or less 2. And that always the rock is stiffer in horizontal direction than in vertical direction. I say correctly, right? Stiffer in horizontal direction than in vertical direction. One more thing to notice here, and linked to the last thing that we saw on Monday. How does anisotropy vary with mineralogy? Can you take a look at the first track and the 6th track and tell me what is making the rock, this particular rock, more or less anisotropic? What? Proportional calcite. So more calcite, what does it do to the rock? Less anisotropic, and more. In this case, this is a source rock with organic matter and with clay. So towards the bottom here, there is less calcite, and there is more organic matter, more clay, and the rock becomes more anisotropic. And this is what we said for those two models of vertical and horizontal, that as you have more compliant phases in vertical laminations, the rock becomes more anisotropic. And you can see measurements for that in this case. So the Poisson ratio, still, it's a little bit more difficult to interpret what's going on. But in this case, what is observed, these are about the same, but the main difference is in the stiffness, in the horizontal and vertical Young modulus. So once you calibrate your well logs with your laboratory measurements, which in this case are these dots, you can increase the confidence in your model and then use the equations that we wrote just 1 second before. This is the exact same thing to what we used. And after you do that, you can calculate the stresses by calibrating the tectonic strains. And I guess this was the isotropic. No, not this one, but finally we get to this stress log, horizontal stress and vertical stress as a function of depth that are needed. In this case, I don't remember if I gave you this, but these are the perforation depths. So they use that in order to tell where to do perforations for hydraulic fracturing, in this case for a vertical wellbore. Yes, Rodrigo.
I just noticed that some of the control points you have on the logs are sometimes shifted from way to another side. So
let's take a look at that.
What is acceptable in terms of quality control if you are comparing your actual data from the logs and your control points?
I guess so that would depend on the quality of the data, both from the log and from the laboratory. In general, you will try to have those of two to match and find like something that fits in the middle. But if you have a lot of uncertainty, also you may expect a higher uncertainty in your answer. So if you have a lot of uncertainty in your inputs, then you will have a higher uncertainty in your output. I don't know if you could define like some threshold value, but it will depend a lot on the quality of the data. Okay, so we're not going to do an exercise with an isotropic case, but you have the theory and you know how it should be done. All right? Okay. Any question? No? You have a question, Jack?
Yeah, can you explain to in your last observation, when you're calculating the isotropy H and affective H in the middle section, like where does that part come from?
Where were what?
Like go back to your
My notes?
yeah.
Okay. So here.
Like right in the middle section, when you're calculating the upper H.
Upper, so this one.
Yeah, so in the middle section, where that part comes from?
This one?
Yes.
Okay.
Where this comes from?
Notice this is part of the effect. This is the overburden. These two terms are overburden. Notice that you have this coefficient Poisson ratio divided 1 minus Poisson ratio.
Yes.
But then you have to correct it also for the anisotropy part. This is just effective stress. This is effective vertical stress. This is Poisson ratio divided by 1 minus Poisson ratio.
Yes.
But there is one more term that you have to add here in order to correct it for the anisotropy of the medium. Before we didn't have this because the medium was anisotropic. And imagine if the medium is isotropic, EH is going to be equal to EV, and this is going to be 1. And we're going to end up with the same thing that we had before.
Okay, but previously we don't have the alpha V, right? Alpha V is also new.
Alpha V is new because these are all the Biot coefficients.
Okay.
That I didn't explain what those are yet, but we're going to see this right after we finish with the general solution of a continuum mechanics problem with linear elasticity. I'll explain that in detail.
And for the last one,
Yeah.
Why in your integration, why do you not include alpha V?
I did not include alpha V because this is total vertical stress. If I wanted to compute effective vertical stress, I would do alpha V minus PP.
You don't have to do that for SV.
No, not for SV. So remember, these are total. In your plots of stresses as a function of depth, remember I want you to plot always as a function of depth total stresses like here. Don't plot effective stresses. Effective stresses are just going to be implied from the same plot. For example, vertical effective stress is going to be this. You see it right there. It's already there. Horizontal effective stress is going to be this for the minimum, and this is going to be the maximum. So as long as you plot the pore pressure and the vertical stress or horizontal stress together in the same plot, already there you have the effective stresses. I added into your projects number 1 a comment. I didn't take points off, but many of you plotted on one plot pore pressure and another one vertical stress. I like that you plot that together because it's more meaningful. All right. So we are done with anisotropy. And now we'll start talking about a general solution for a continuum mechanics problem with linear elasticity. And well, let me wait a minute. All right, let's continue. Let me move this over here. What we want to do now is to find a general solution for a continuum mechanics problem, and in particular we're going to use linear isotropic elasticity. You could extend this on your own for anisotropic elasticity. It's not too difficult, but we're going to see just how it is done for linear isotropic elasticity. Do you remember the three basic equations that we need to solve any problem of continuum mechanics? The first and most important one is equilibrium, just to make sure that things are not moving. And we derive this equation the first or second day, and this is equal to the divergence of the stress tensor plus any body forces, and this has to be equal to 0. This is the short form. These were the Cauchy equations. Which was the second equation that we saw? Kinematic, very well. And the kinematic equation allows you to compute strains as a function of displacements. And we can shorten this equation instead of writing all that big matrix with this vector notation that you don't have to remember by heart, but here it's just a lot more useful to me to write it in a compact manner, where this T means transpose, but basically tells you what are strains as a function of displacements. And remember that this particular equation is valid for small strains. And the last one is the constitutive, and we have spent quite a bit of time with the constitutive. We saw first isotropic elasticity, and then we just finished seeing anisotropic elasticity, and later we'll add poroelasticity to it. But it's all part of the constitutive equations. And constitutive equations allow us to link stresses and strains through, in this case, stiffness matrix. Okay, in this case, this is linear elasticity. Okay, we're not going to do this right now because it's going to take a long time. Probably we'll do it later on. But what you can do here is you can put this strain, you can put this equation. Let's say this is 1, 2, and 3. You can put 2 into 3, and what results from that is going to be sigma, and you can put all of that into 1, which is equilibrium, and as a result, you're going to have an equation that just depends on displacements, right? Because we're going to put this over here, then you will have stiffness times gradients of displacements, and then we put this inside there, and then we have divergence of gradient, and it's going to be an equation just about displacements. So if you do all of that, the final answer is going to be this. It's going to be an equation that just depends on displacements, and this is a displacement vector, and it's going to look like this. So look, the F is still there, And how many equations do I have in this equation that I just wrote? If we were to expand it. How many, David? 3, right? Because it's a vector. So we have 3 equations. Where lambda is what is called the first Lamé parameter. And and is going to be equal to m minus 2 times the shear modulus, and it's also equal, if I remember correctly, let me check this later, okay? But if I remember correctly, this is like this. I heard yes, someone remembers that? I believe this is it. Let me check it quickly. G is the shear modulus. Okay. And shear modulus is M modulus divided 2 times 1 plus Poisson ratio. Yes, that should be correct. And G, mu, what did I write mu and G? Sorry about that. So, my eraser. I should write just one of those. Oh no, this is on. It's okay. Oh, here it is. So mu, and let's just use mu. Mu is equal to G equal to M modulus divided 2 times 1 plus the Poisson ratio. Okay. This equation here is what is called the Navier's equation for linear elasticity. In this case, this is linear isotropic elasticity because we just have 2 parameters, and that fully defines this medium. If I want to solve a problem of continuum mechanics with linear elasticity, this is what I have to solve. For those of you that are more familiar with reservoir simulation, in reservoir simulation, you solve for pressure. That's your unknown. In mechanics, you solve for displacements. That's going to be our unknown. But basically, you just have to solve this differential equation. Okay? All right, so let's see how we solve that equation. We're going to see several methods in order to solve these equations. First, you could have an analytical solution. You put some boundary conditions and you solve the differential equation. But you have to be very good at math in order to do that, and your problem also has to be relatively simple. Otherwise, it's very difficult to solve it. We're going to see solutions of this type of analytical solution, for example, for a wellbore or a circular cavity, which is called the Kirsch equation. We're going to see stresses around a crack, which is a Griffith solution. For stresses close to a crack, we're going to see, or I'm going to tell you to see, the Snedden solution. But those all are going to be analytical solutions for relatively easy problems that we can use in order to tell what are the stresses and strains around a circular cavity or an elliptical cavity. There are some other methods that we're not going to see, but like, for example, the Airy's equations that allows you proposing a solution to derive what is the actual solution for a problem, and actually Kirsch is based on that Airy's equation. But we're not going to see that, okay? That's one method to solve this particular equation. And another method is to find a numerical solution. And for a numerical solution, we're going to discretize the domain, and we're going to solve the unknowns by solving linear equations. We can solve this with finite differences similar to a problem of reservoir simulation. The diffusivity equation for isotropic media and for one-phase fluid flow is relatively easy, and we could solve it with finite differences in 2 pages. But for elasticity, it's a little bit more complex. And because you have 3 equations, and then it gets a little bit more complex. Even in 2D, you have 2 equations. So we will not go through this one. We'll use another solution, which is finite elements, which actually is very complex too to derive it entirely. But we're going to use a free software which is going to allow us to solve these problems for an arbitrary domain, arbitrary boundary conditions, and to solve it numerically with finite elements. So I'm not going to go in detail about the analytical solutions, okay? I can give you references where you can see that. The book from Jagger is very good for that. It has the solution step by step of the analytical solutions. And we're going to jump directly into the finite element solution, but I'll give you some of these analytical solutions so you can check that your numerical solution is okay. And that's basically project number 4. In project number 4, I'm going to ask you to solve for stresses and strains in a circular cavity, and compare that to the Kirsch equations. And in problem number 2, I'll ask you to simulate a half domain as if you had a fracture in the middle and tell me what are the stresses around a fracture. So in the wellbore, you're going to put stresses outside. And in the fracture problem, you're going to put a pressure in the fracture, and you're not going to let the boundaries move. The advantage of the numerical solution is that you can put any type of boundary condition and still you'll get a numerical solution. Analytical solutions, you need to have a very specific shape and very specific boundary conditions. Otherwise, the solution is not that easy. All right, so for the analytical solution then, I'm going to direct you to the literature to see how you find that. We'll talk about the numerical solution. Jack, you have a question?
Yeah, so it's one of those concept questions. So when you combine, like in the second diagram you draw,
Yeah.
does the boundary also exert a stress onto the?
Here, the pressure, yes, is going to be a stress boundary condition. And in this case, you have stresses from outside.
But you are saying that the 3 other sides of the second problem
It's fixed. It's not moving. Yes.
So that also exerts a stress onto the.
There's going to be a reaction at all these points. Yes, because you push in one direction, there has to be a reaction at those points so that doesn't move. Okay, we'll see in detail the domains of these two, about how to solve them. But the first thing that we're going to do now is we're going to see the theory of the finite element method to see how we solve these problems. Again, our objective is solve for displacements. Once we have displacement, we calculate the strains. Once we have strains, we calculate the stresses. Once we have stresses, we can answer if this is a failure or not. Once we have stresses, another example, you could also say, what is permeability if there is a relationship with stresses? But this is the direction in which we're going. Okay, so let me put this away. We're going to start with the finite element method. Did any of you guys take a class in finite element method? No? Well, I strongly recommend that you take one here. When I was in grad school, I didn't take a finite element class, and I regret for that till today. Here, I know that there are two very good classes in finite element method. One is in civil engineering by Professor Kalivokas, and another one is in aerospace and engineering mechanics by Professor Wheeler and Professor Dawson. In engineering mechanics tends to be a little bit more mathematical, more into trying to look for the convergence of solutions and prove that there is a unique solution. In civil, it's a little bit more applied. But here we'll discuss, very briefly the finite element method. Okay, and the first thing we're going to do is to do an analogy of the finite element method with what is called the principle of virtual work. So let's say that we have a bar, and here the bar is supported on this point, and it's now moving down. And I put a weight here. And my question is, what is the force I need to put on the other side in order to equilibrate the weight? And let's say the length to the weight is L1 from the point of support, and the length to the point of the force is L2. So what is the force? I'm sure you guys know how to do this. This is statics 101. I want to know what is the force. What does it depend the force on? How many times the weight? And how did you do that? How did you get to that solution? Okay. So, but what has to be equal?
W times L.
Okay, and what is W times L? Well, it would be angular momentum or the torque, right? The torque, angular momentum. Let's just call it equilibrium of angular momentum, but this is the same as the torque. We know that F times L2 has to be equal than W times L1. So for those of you guys that didn't take statics, and in statics what we do is we choose a point, like for example this one, and we calculate. Then the torque is going to be L2 times F, has to be equal to W times L1. That's why when you have a long lever, the force that you have to make in order to lift the weight is going to be proportional to the ratio of the distances just from the equation above, L1 divided L2 times W, right? So if L2 is 5 times larger than L1, then by applying a force on F, you can lift the weight W with a fifth of its weight. All right. So we're all in agreement with that? All right. Probably you have seen this, but what you're going to see now, probably you haven't seen it yet. There is an alternative method to solve this problem. And this alternative method is based on energy. And it consists on the following. We are going to assume that we make a tiny displacement, which may not be real, but it's a tiny displacement of that bar. So it moves an angle theta to the left, and that's the same angle theta on the right. By energy conservation, if this is under equilibrium, what is going to be the work done by the force W? Remember, work is force times distance. What is the distance that W went down? No. Tangent. Very well. Is the force times that distance. And that distance is L1 tangent of theta. Force displacement. That's work. And that has to be equal to the work done by F. And notice that this one has a longer displacement. And that's going to be F. The displacement is going to be L2 times the tangent of theta, where these two are displacements, and we're going to call it a virtual displacement because we just made it up. But it's something which is called kinematically admissible. I could have done it, I did it this way, but I could have done it that way, and it would be the same. All right. So the tangent is in both sides. So from here, I get that F again is going to be L1 divided L2 times W. It's the same solution. And using this principle is how we're going to solve our equations. And this is what is called the principle of virtual work. Why virtual? Why virtual? Because we apply a virtual displacement. And that force times the displacement give us a work. So that's why it's called the principle of virtual work. All right. So we're going to apply this now to a general problem. And it may look a little bit more complex in the math, but it's exactly the same what we just have done. Okay, let me put a line here. For this general problem, we'll draw what in continuum mechanics is called the potato problem. So it's an arbitrarily shaped three-dimensional body. It looks like a potato. It has a volume, which we're going to call it omega. It has a three-dimensional surface that we'll call it lambda. And that surface at every point has a normal vector that characterizes the surface, and is the vector n. So this is an arbitrary domain. And what these lines mean over here is that the solid is anchored at this location. So for example, to this particular medium, it might have a weight. I could put a force somewhere over here. I could put a stress somewhere over there. I could put anything to it. Okay? All right. So let's see how we apply the principle of virtual work and how we get our equations to solve the finite element problem. First, we're going to start with equilibrium. This is the most basic equation, and we have to respect it all the time. Then I'm going to just move one of the terms to the left side. And what I'm going to do now is, remember that this is an equilibrium equation. This is a force. So therefore, these are stresses. And these stresses can be thought as the forces that we had before. Stresses inside this body. All right. So what we're going to do is we're going to multiply all those stresses times a virtual displacement. Similar to what we did over here, but now in general, this is a virtual displacement that we're going to call delta U, where the delta means virtual. And I do the same on the other side to guarantee that the equal sign still holds. And remember, this is a virtual displacement, and it is not just one displacement, it's a displacement field in the entire 3D body. And since this is a body, it's not just a point, and it applies to the entire body, I can apply an integral over the entire volume. All right. Now that I have this integral of virtual displacement times actual stresses, what I can use is Green's theorem. That, if you remember Green's theorem, it helps break down a divergence term into two terms, one an integral of volume and another one an integral of surface. So this is just math. From what I'm going to write now, from here to what I'm going to write now is just math, okay? It's not mechanics, but it has a mechanical interpretation. According to Green's theorem, I can write this as the gradient of the virtual displacement times stress tensor and plus an integral over the surface of virtual displacements times the, do you remember what this is, guys? Stress times n. And the other term remains the same. Anyone remembers that? You did that for project number 2, number 3.
Stress projection on a plane, right?
Yes, it's a stress projection on a plane. This is actually what is called a traction vector, but it's the stress on a plane. This is the direction of the plane. This is the stress. You multiply those two, and that's the result of the traction vector on a particular direction. And notice that that traction vector now is applied over the surface of this volume. Okay, so from here, what I'm going to do is I'm going to write this term a little bit differently. What is the gradient of a displacement. You remember how we derived the kinematic equations? That strains were the gradient of a displacement. The equation is a little bit more complex. You remember when we did a Jacobian, and we said if we take the Jacobian of the displacements, we get the strain tensor plus the rotation matrix. But if we move a few things around, then we just get the strain tensor. Well, the gradient of a displacement field is going to give us strain if we manipulate the equations a little bit, and this is going to be the strain of the virtual displacement times, and this is, I'm going to explain what this is, just give me some time, vectorial tensor, vectorial product, the strain tensor, which is a function of displacement, actually the real displacement, not the virtual displacement, and this is going to be equal. I'm going to just move this one to the other side, and it's going to remain the same. Actual stress times direction plus the virtual displacement times the body forces. And this is my final equation. The term on the left is strain times stress. And we're going to see that this is strain energy. The first term to the right of the equal sign is stress boundary condition. And this is just the body force. This equation written with these virtual displacements here, there, and there, it's what is called, wait, I forgot something in here. This is the gradient of the virtual displacements. This equation as written here is what is called the variational form of the Navier equation in this case, and also known as the weak form. And this is the equation that we need to put in the finite element method in order to solve it. But again, let me remind you about the analogy that we did before. We want to use a method that does not solve directly for stresses based on equilibrium, but that solves that based on a virtual displacement. We multiply that virtual displacement, which in this case goes to strains, to the forces, and to whatever is around the body and inside the body as a body force. We do the integral of all of that in the entire domain, and we'll be able to solve the equation. And I don't have any more sheets. Anyone has a blank sheet, which is blank with no lines? No. Let me see if I find one in my notes. Okay, I've got one. I'm going to use this one. The unknowns of my problem are the actual displacement. You remember that was the same thing that we needed before in the Navier's equation, and also the virtual displacements. But we don't care about the virtual displacements because they are virtual. It could be anything. What we really want is the actual displacement. So with that, we can calculate strains and then stresses. One more thing, I told you that I will explain what is the tensorial product of the strains times the stresses. This is going to be equal to the tensorial product is like a dot product, like for a matrix. So, for example, dot product for two vectors, you multiply element by element and you add them up, right? For the tensorial product, it's the same, but you go through all the elements in the matrix. So, in this one, for example, it's going to be the virtual strain epsilon 1,1 times sigma 1,1 plus the virtual strain epsilon 2,2 times sigma 2,2 plus and so on until you get to epsilon. It would be, let's say, the shear 2,3 times sigma 2,3. So you go through every single element of the matrix, you add all of those up, and this is that tensorial product. And as we were saying, this is strain energy. For a fluid, energy is equal to pressure times volume. And if you know this, in our case, this is stress, which is similar to pressure, not exactly the same. And in our case, we're going to have volume, but this is going to be, this is just total energy. If we divide volume by volume, we get energy by unit of volume. And this is dimensionless, and this is strain, and this is how it works. So a strain times stress give us energy by unit of volume. All right, so I think we have done enough today. And what we're going to do on Monday is to actually code this equation into a software and solve it. So if you can bring your computer, your laptop, please do it, and previously install this software, FEM++. For those of you that like Python a lot, I recommend that you use another type of software which is very similar and has a lot more of support, which is called Phoenix. And the website is phoenixproject.org. I wanted this time to use Phoenix, but it just works a lot better with Linux or with Unix system. So if you have Mac, probably you can run it very well on your Mac. But if you have Windows, that's going to be a little bit painful, especially if you don't have administrator rights. So it's a lot easier to use this FEM software. And probably, again, if you want to use Phoenix, you're welcome to do that. But FEM is very similar, and it's a lot easier. In the future, if you want to move to Phoenix, having learned FEM is going to be a lot easier. Okay? I'll see you on Monday, guys. Thank you.